Alright, so what we are going to talk about now is something that it's kind of starting to get us to the point of being able to use some factoring tools that we've learned in the past. But we've got to do about a day worth of other stuff before we can get there. Okay, so this is a way of trying to solve and find out where a parabola crosses the x-axis. Okay, so we've talked about y-intercepts, we've talked about vertices, right? Those are two things that are critical for every parabola. Another thing that is critical for parabolas is the x-intercepts. Okay, and if we can find those, we're going to be well on our way to being able to graph any quadratic very quickly. Okay, so every quadratic equation is an equation that can be written in the form ax squared plus bx plus c equals 0. Okay, so what we've been talking about lately is it equaling y. So we've had two variables, x and y. Here, we have just one variable, x, okay, equal to 0. What that means, if you guys remember back to like the first time that we started graphing things, I gave you a visual of if I want to take an equation, any equation ever written, and I graph the left-hand side. I take the equation, I say that left-hand side is y equals something. And then the right-hand side is y equals that. And I graph both those at the same time. Graph the left-hand side, graph the right-hand side. You're going to have two curves. Okay? You might have two quadratics, you might have two lines, you might have a quadratic and a line, you might have whatever. Doesn't matter. Okay? The answer or solutions to the equation are the x values where those things cross. Okay? So let's say that I have, we'll just do a quick example here. Let's go to Desmos. Let's say we've got the equation, let's say 4x squared plus 2x minus 1 equals, let's say 7. Okay, let's say it's equals 7. Now, it graphs this. Don't know why it's good. I don't want to graph it. But what happens here is if I'm asking what are the answers to this? What are the answers to this? The answers are the x values that make this true, right? So what we do is we graph the left-hand side. Y equals 4x squared plus 2x minus 1. And we graph the right-hand side, which was y equals 7. Does that make sense? Now, the x value right here of negative 1.686 is the answer to this equation. So if I were to take this number here, or this, see if I can cut and paste it, Control C, V, okay. Let's just go ahead and make this A real quick, just so I can do the substitution. So we saw that the answer is negative 1.686. If I make A negative 1.686, okay, does that get out? It's because it's rounded, it's only giving me out to 3 decimal places. Is that pretty close to 7? Okay. I really don't like you. That's really close to 7. All right. So if I try this number, 1.186, 1.186, since positive, there we are again. If we had this exactly the full decimal, this would go exactly to 7. So the solution to any equation is where the two graphs cross, the x value of where the two graphs cross. What we're going to talk about right now is when we have y equals ax squared plus bx plus c, so some quadratic equaling 0, the two equations are then, this here is going to be a parabola, and y equals 0. What's another name for the line y equals 0? If I look at my graph here, y equals 0 is the what? Fishbowl. Huh? Did you say fishbowl?
No, the axis is symmetry.
It is an axis, not the axis of symmetry though.
What?
If y equals 0 is the What were you saying? Jenna, what'd you say?
Symmetry.
Not the axis symmetry.
Because x equals the line of symmetry.
Right, so if y equals 0, that would be this red line, right?
It's, I don't know.
What do you call that red line in the in the two
Oh.
in the coordinate plane
Hold
here?
on, wait. No, I know it. Wait, are you just talking about the y-axis? Is that what you mean?
In this case, though, this is the x-axis. So whenever we say y equals 0, that's the algebraic representation of the x-axis, right?
No, it said it was a laser.
So when we ask this question, ax squared plus bx plus c equals 0, we're asking where does the parabola cross the x-axis? And when we cross the x-axis, those positions are called x-intercepts. Okay, does that make sense? Okay. X-intercept, so Austin's probably never had this situation happen, but like if a quarterback was to throw a ball to a receiver and he cuts through the path of the ball and catches it, and the receiver doesn't, that's called a what? An interception, okay? Because you pass through the path of something, correct? Okay? So when we have an x-intercept, that means that our curve is passing through the pathway of, in this case, our x-axis. Okay? So when we have parabolas, there are three situations that can happen. Okay? Now these could be upside down, they could be concave down, so they could be like with a maximum, so going kind of this way, right? Okay. But these are the three types of solutions you could have. You could have a situation where your parabola does not intersect your x-axis at all. So in that case, we would have what we call no real solutions. Okay? Meaning there are no real values on this x-axis that become solutions. Okay? We can have one solution, and that's where your vertex is actually on the x-axis. Okay? When we have that one solution, the work that we do in the next several days, that solution will actually show up twice. Okay? So if we have a graph like okay, so there we see we're just touching the x-axis at 2, right? When we go through the algebra that presents that 2 to us, we will actually see that answer show up twice for us. And that will be the identifier that tell us that we just touch the x-axis, we don't pass through it. Or you could have two solutions where your graph passes through the x-axis, dips down, finds its maximum or minimum at some point, and then back up. Okay, so that case in that third picture, it's going to be a minimum. If it was reflected, if it was looking like this, okay, then that would be a maximum. But you're going to have two x-intercepts. Is that okay with everybody? Okay, so, huh?
Yes.
Can I keep this?
What? No. So when we solve equations of lines, okay, if we were to have a linear equation, there are situations where you can have one solution or no solutions. Okay? Most equations that we've dealt with lines have had one solution. So if I say something like, what is the solution to 2x plus 3 equals 5? The solution to that is 1, right? Okay? And then you have, in terms of counting how many solutions we have one finite solution. If I had something like this, when does 2x plus 3 equal 2x minus 2? If I go through and solve that, that gets me 3 equals negative 2, and that makes no sense, right? That's a false statement. So how many solutions do I have there? None. Okay? So you can have, in a linear equation, because of the largest exponent being a 1 right there, you could have one solution or 0 solution. When we talk about a quadratic equation, the exponent here is 2. So you could have 2 solutions, or you could have one solution, or you could have 0 solutions. Does that make sense?
Yeah.
Okay. What if that was a 3? What if we had something just kind of, we're not going to talk about these very much, but let's say I had something like ax to the third plus bx squared plus cx plus d equals 0. How many solutions do you think I could have there? If that's a 3, going off the pattern that we've seen previously. I could have 3 or
More. Less.
2
Yeah.
or
1.
or
0.
Okay. And we're going to get into eventually coursework that would actually tell you with a cubic like this, you can't have that 0. Okay. There will automatically be at least one solution. We'll talk about that kind of stuff later on, and maybe a integrated 4 or something like that. Okay. So the first thing I want to do today, or in this section, is talk about how we go through and determine those x-intercepts for a specific or special type of quadratic equation. And this is the first type of quadratic equation that we've seen when we were graphing them. If I had something like, let's say 3x, let's say 3x squared equals 0. And I asked you, in that situation, what is the x value that makes that true? It would be 0. I hopefully you can see that. Okay, what do I put in for x so that the left-hand side turns into 0? Well, the only thing I can do that is 0. You could do it this way, though. You could divide both sides by 3, and that's going to give you x squared equals 0, right? Okay, what undoes a power of 2? If I have x squared, how do I get that down to x to the first? You can't divide it. Like let's say that I had 9. How do I get 9 down to 3? Or if I had 16, how do I get 16 down to 4? Okay, so if I divide this one by 3, divide that one by 4, divide that one by 5, so that would be different each time. Okay, I'd have to have a different rule for each one of those. You guys ever seen this before?
Oh yeah, but I can't remember what it's called.
Because that's not division. Division doesn't have this little square root. So if I take the square root of x squared, okay, they cancel each other out, and it leaves me just x. And now, so basically the square root, what the square root is, it's a symbol for another number. Okay, think about like how pi is. Okay, we see pi over here. Does anybody know what the number for pi is?
Emily?
Emily, tell me what pi is.
3.14.
Okay, and that's et cetera. Right? It's gonna go on forever and never repeat, never end or anything like that. So there's no way you can ever write that down, right? Okay, at least the whole thing. You can write down 100 digits of it, but you can't write down the whole thing. So to represent that whole thing, because when we work with circles and we work with very precise measurements, we want the whole thing. We have to use a symbol, because if I change it to 3.14, it's no longer a pi. It's an approximation for pi. Square roots are the same way. Okay, square roots end up being most of the time what we call irrational numbers. They do not end and they do not repeat. Okay, some of them do end, like square root of 9 is 3. And it ends at 3, right? Okay.
Wow.
But if I go square root of 2, that's like 1.4144, something like that. So let's see what square root of 2 is real quick here. Okay, so square root of 2 is that number right there. Does anybody know what that really means? So it's a radical 2, or square root of 2. That symbol up there is a symbol. It's basically an image or a picture that actually means 1.414213562337. Okay, that's what that radical 2 really means to us. But does anybody know why, or what that's doing? What that 1.41 number is? Basically asking, what is the definition of a square root? Okay, so the answer is no, right? So let's talk about this. Let's say, okay, so if I'm doing square root, a lot of times when it's first introduced, we put a little number out in front. Maybe you guys have seen this before. We put like a little 2 right there. And that's referred to as an end. We don't do any like calculations with that 2 out there, okay? It's called an index. And basically what it's doing is it's telling me how many times I'm going to multiply something together. Okay? And because it's a 2, it means I'm going to multiply something together 2 times. If it was a 3, it'd be telling me to multiply something together 3 times. 4 times 5 times. But what this is, okay, so it's a square root, okay? What that means is if I take this number right here, this 1.414 number, and I multiply it by itself that many times as the index indicates, it should end up giving me the number underneath the radical. So if you ever wonder, okay, what number can I multiply by itself twice to get 2? That number is 1.41421356337.
Okay, so when you write that, do you write it on top of like the?
You're talking about that too?
Yeah.
So like a clean way. A lot of times you just write the 2 and then like most people kind of do it that way. If it's not written, we automatically know it's a 2. Does that make sense? So if it's not written in there, if I just say this here, then I automatically know it's a 2. Okay? So to prove this to you, let's take this number. Take that number and then multiply it by itself. Okay, now understand, so it gets 1.99999999999, right? And the reason it's not giving me 2 is because that number goes on forever like pi does. Does that make sense? And right now I'm only able to capture 10 decimal places, so then it doesn't, when it multiplies together by itself, it doesn't give me the complete 2. There's a little bit of rounding error there. Does that make sense? Okay, so give me another number.
69.
So let's go square root of 81. Let's go 80. Okay? So that means if I take that number right there, because I'm hoping that at some point you grow up. So if I take that number and multiply it by itself, in this case, there's not much rounding error, and you see that it does indeed give me 80 there. Does that make sense? Okay. So let's do, I believe we've got a cube root ability here.
We got 2 minutes. Hey, don't
Okay, so if I put a 3 out here, and then let's go 8 real quick, and it gives me 2. So what that means is that if I take 2 and multiply it by itself 3 times, take 2 and multiply it by itself 3 times, it gives me the 8. Does that make sense? Okay. If we go with, let's just do like 7, cube root of 7. Okay, so now I'm going to take that number right there, and I'll multiply it by itself 1 time, 2 times, 3 times, and does it give me something pretty close to 7? I'm going to quit. So, that idea of square roots, cube roots, that we need that understanding for what we're going to do with the quadratics. Okay? If we had a full 15 minutes, we would obviously go into some examples. You see it right away. We will pick up with that on Monday.